Oh, we're rolling. So, welcome. Good day. How the heck are you? Uh, Today we're going to talk about, learn about, visit with, spend some time with a little thing we like to call the definite integral. Okay, you'll notice that right below where I'm writing is this thing. This is what we've been sort of using as we've been working through the last couple of days, using the fact that we can find the area of a little box, so the f c sub I times delta x, and we sum all those up. Okay. The difference between what we've been using and what is written here, okay, we've been using as n approaches infinity, and this is talking about as this little weird thing here goes to 0. It's a delta. So this is the partition, is what it's called. So what we've been doing is we've been making sure that all of our boxes are the same size, they're all the same width, and it really doesn't matter, as it turns out, is that if basically the boxes aren't the same width, we get the same result. So what it turns into is we look at as the partition size turns into, approaches, that's the word, 0, then this limit gives us the area. Yeah, so the limit is the partition size, which is just, basically the idea is that we want our boxes to get as small as possible. They don't necessarily need to be all the same width. Some can be a little bit smaller, a little bit bigger, but they are all approaching 0, and that gets us the area underneath the curve. Well, it turns out that this approach here can, or does, and we'll use from here on in, lead to this. Okay, so all this thing that we've been doing that logically makes sense, that we can, find the area of a rectangle, and we can sum up all the rectangles. We can also use what's called the definite integral to solve. Okay, so it's a definite integral. You'll notice the little symbol looks a lot like the antiderivative symbol that we used. Well, you know why? Because it is. The only difference is now we've got a and b, and you might recognize a and b from our work with the summation formulas with the sigma stuff, because that's the lower end point and the upper end point of our interval. Okay, so we're not going to necessarily get to like the nitty-gritty about how that works today, how we actually use that. We'll save that for the next time with the fundamental theorem of calculus, but we're going to use the concept of finding the area using the definite integral today, right now. Whoa, so there's some properties, lots of information right here. So it turns out that if we try to find and think about what this means, like sort of means the area under the curve, okay? So we've tried to find the area under the curve of this function from a to a. It's 0. That seem reasonable? Okay, if we don't go anywhere, we get no area. The integral from a to b of the function is just the opposite of the integral from b to a. Okay, so depending, the actual which numbers on top does make a difference in terms of which way we go. All right. If we're trying to get from a to b, we can do it in steps. We can go from a to c, and then we can add to it from c to b. Okay, C is somewhere in between A and B is what we're should make note of that. C is somewhere between A and B. All right. So we can break it into pieces if that sometimes that'll help us out. If we have a constant times a function, we can pull the constant right out in front, sort of like what we did the other day. Okay, constants just come along for the ride. If it just makes it any easier for you, you can get those out of the way. Sometimes that's helpful. Okay. If we have a couple of functions added or subtracted from each other, we can just do the separate integral and the separate integral, and then add or subtract as we go. So, not a whole lot of thing there, not a whole lot of extra crazy information, just lots of properties of them. Which one's probably one? This one's probably this one's a big one we'll use. That one's a big one we'll use, and this opposite idea we'll use a little bit. Okay. So those are some properties. Let's try a couple of little things. Okay, with these. So I'm just going to tell you, in the works that we're going to do today, I'm going to tell you that the definite integral of x cubed from 2 to 4, so again, sort of we'll think of that as, for right now, this is the area under the curve of this function x cubed. So x cubed, remember, looks like that. From 2 to 4, we'll say is that. So this area right here is 60. The area under the curve of y equals x from 2 to 4, so it's a little triangular sort of region. Yeah, well, not really. It's trapezoid, isn't it? It's trapezoidy region is 6. And the area under 1, okay, and 1 is this. So that's the axis. There's 1 from 2 to 4. That's the rectangle. Okay, so that area is 2. All right. So we want to use that information to figure out what's the area under the curve of 3x plus 5. Okay. So if we do this, we'll just, we're going to say that this is 3 times the definite integral of x plus 5 times the that 5 times the definite integral of 1. That works. And I should put the dx in there for good order. So the definite integral of x is 6, so I get 3 times 6. The definite integral of 1 is 2, and so I got plus 5 times 2, 18 plus 10 is 28. Okay? Better when I'm on the other side of the room, but I can't do that with this situation. So this one, should I leave that one for you? All right, I will. Yeah, I heard you. Heard you loud and clear. So we'll leave this one for you to try. Okay, just so that we make sure that we have some idea what's going on. You just break it into the little pieces, and off you go. Okay? So there's that piece. Good. So, set up a definite integral that can be used to find the area of the shaded region. And I know what you're thinking. You're saying, hey, no region is shaded. How do we do that? Well, let's get a little shady pen. Let's go with green shading. And let's shade in very carefully this region. Right there. Okay. So pretend that was a really good color, and I actually stayed above the x-axis as we're talking about this. Okay. Typically, when we're finding definite integrals, when we're finding areas, we usually find the area between the function and the x-axis. So if I were to find, integral for me, this one would be that. If I were down here, it would be the area just between the x-axis and that. But we're just going to worry about that little piece right there. Okay, let me get back my regular colored pen. So, wait, there we go. All right, so to set up a definite integral that can be used to find the area of the shaded region, there's my definite integral sign. There's my function, and I'll just write it all out. X times x plus 2 times x minus 1. Okay, dx. Dx is just the operator. It just tells you that we're integrating the x variable. Okay, so the combination of this sign and that sign is sort of like, multiplication symbol or division symbol or any other operation, a square root sign. This is just saying we're integrating with respect to x. Okay, so just like, and it goes away once we actually get to the place where we have an answer. So we're going to integrate from, in this case, it looks like that's negative 2 to 0. So the lower limit goes on the bottom. The upper limit goes on the top. Set up a definite integral that can be used to find the area of the shaded region, and we're done. Okay, so for today we're done. Tomorrow we'll get to a place where we can actually figure out how to find that answer. What actually all this stuff is. Where the 60 came from, where the 6 came from, where the 2 came from. We'll get to that when we get on to the fundamental theorem of calculus. For today, we're just looking at the concept of it, moving beyond the sigma notation, the fact that there is a mathematical operation that does fairly quickly the same thing that we've been wrestling with for the last couple of days with the sigma notation. Okay? And it's pretty clever that someone figured that out. So, that I think is about what we're going to learn about definite integrals today. Okay? So, that's what we're going to work on tomorrow. That's that, and I think that's about it. So, thanks for watching. If you learned something, we'll talk to you real soon, and I guess that's it. Oh yeah, under 9 minutes. We're going to go exactly 9. You ready? 3, 2, 1.